Then we've got the H plus on the inside, and I'll make that guy green. Right, so there's H plus on the inside of that glass electrode. That is in here. Right? We have a known amount of H plus on the inside of that glass bulb. Right? And this glass membrane, which I will make in purple, right? That glass membrane is where we're going to start to develop difference in the H plus concentration on the inside versus the outside. Okay? And then over here we just have the inner reference glass electrode. So all the concentrations are going to be constant except for those in the analyte solution. So the only difference between one pH measurement and another is when we're looking at the analyte solution. So what's going on in the outside, right? What's going on in the blue? The only analyte that binds selectively to this glass membrane is H plus. Right? H plus is the only thing, and we're going to put that in quotes, air quotes like that, that is able to get through that membrane. The two reference electrodes are going to measure the electric potential across that glass membrane. All right, so let's take a look at this. All right, so we've got our reference electrode number 1. Right? It's going to be a saturated calomel electrode. We have the external analyte solution. This is the thing that we are testing. And that's in our beaker. We have another glass electrode over here, which is our internal glass electrode. This is the stuff that is going to be at the inside of the solution. This is where our glass bulb is going to be, that glass membrane. And so we're looking at this potential difference here, right? This guy over here is just our saturated calomel electrode. It's got a junction potential that should be relatively constant. Over here, we've got another AgCl electrode, and our chloride concentration is 1 molar. We're going to have an activity of hydrogen on one side, on the internal side, and one on the external side. So it's what is my concentration of H plus on the out? There's my glass membrane. What is my concentration of H plus on the inside? Right? This junction potential right here is measuring how many H pluses are on the left side versus how many H pluses are on the right side. Right? And if I have an uneven distribution of plus charges, that's going to be a potential or a voltage. So we can take this equation and we can rewrite that. And it's going to be E cell is going to be E naught minus 2.303 times RT over F times the log of 1 over the activity of the hydrogen ion. Right? So this looks very similar to that electrode of the first type once we boil it all down, right? Which means that our pH of our unknown is going to be the pH of our standard solution, and usually we're going to make that pH of our standard solution, if this guy is 1 molar HCl, well, what's our pH for something that's 1 molar? So if this concentration is 1 molar on our standard, our pH is going to be 0. So our pH of our unknown is just going to be our standard minus our unknown voltage divided by 0.2303 RT over F. And so that's just how we're going to calculate that. The fact that temperature shows up in here is why we're oftentimes going to need to calibrate for temperature if we've got a pH probe. If you remember the one that I showed you, it had a little temperature sensor in there. It's oftentimes just a little bimetallic junction, but a good pH probe is going to correct for temperature because, one, this is going to change over time, right? Your Nernst equation is going to change over time. Not only that, but your K is going to change over time. And even your pH scale is going to change over temperature, right? So your pH scale, if you get that thing up to right about the boiling temperature of water, your pH scale can change by plus or minus a couple of pH units. It's not going to be a 0 to 14 scale anymore. It's going to be like a 0 to 13 scale. The salt bridge and a pH combination electrode. The outer electrode solution is connected to the analyte solution via a porous salt bridge. Examples of salt bridge and combination electrodes can be a ceramic plug, which is very common, or it can be a platinum diaphragm, which is way more uncommon because it's hard to make. It's also expensive. Right, so what's connecting these two things is the salt bridge. Usually it's going to be just a little bit of ceramic down here at the bottom. What is the nature of this glass membrane? This is definitely something you should know. The glass membranes inside pH probes must be slightly conductive. Glass membranes in pH probes are built from amorphous silica. So amorphous just means it doesn't have a regular crystalline structure. So if you look at this transmission electron micrograph, you have a nice crystalline region over here where everything is nice and ordered, follows nice neat rows, right? All these guys are going across, all these guys are going diagonal, and then you have this kind of random area, right? And that random area is the amorphous region, right? It's irregularly ordered, and it's going to have some pores or holes in it that are coated with negatively charged oxygen atoms. So you see this little oxygen atom over here. He's got a negative charge, right? Glass is just SiO2. It's a network solid of those things. I'm going to have some pores, these empty spaces in here. And on those empty spaces, I've got lots of these oxygen atoms. Well, if I'm a hydrogen and I've got a plus charge, I'm going to be attracted to that pore, aren't I? Now, the downside is that monovalent cations like sodium, right, are going to be able to move sluggishly through those pores. Right? It's going to be slightly conductive. Right? Crystalline silica is not conductive because it lacks pores. If we look at this cross section of what this glass membrane looks like, right, we have our outside where I've got some H pluses, and I've got my inside where I also have some H pluses, but I know how many H pluses I've got. And we generate what's called a hydrated gel layer. And that hydrated gel layer is kind of where the solution comes into contact with that silica surface. Right? The two surfaces of the pH sensing glass membrane absorb water in a hydrated gel layer. Metal ions or cations in these layers are going to be able to diffuse into and out of that glass and into solution. H plus, because it is the tiniest of your cations, can diffuse into the membrane to replace metal ions. The reaction in which H plus replaces the cations in the glass is called an ion exchange equilibrium. Okay. So I've got my internal solution, it's got some H pluses. This is that gel layer, my hydrated gel layer. Right? I can move this H plus in, and if my H plus moves in, well, it's able to bump something else with a plus charge out. Right? It's able to move those out. The pH electrode responds selectively to H plus because H plus is the ion that diffuses most effectively in that hydrated gel layer. Right? Remember, these pores are teeny tiny. So something big like, I don't know, a cesium, right? So here's some big chunk in cesium, right? It's huge, right? That cesium just cannot get into one of those teeny tiny pores. And if it did, it wouldn't be able to move through it very effectively. So something small like hydrogen is the one that's easiest to move in and out. Now, some of you might be going, oh, wait a minute, well, what about other small cations? How selective is selective? And we're going to talk about that later on because this glass membrane can be tricked and fooled by something like sodium. Right? Potential differences across the glass membrane measured by the inner and outer silver-silver chloride reference electrodes. It's going to depend on the chloride concentration in each electrode compartment and the potential difference across the glass membrane. The chloride ion concentration is fixed in each compartment, and H plus is fixed on the inside of the glass membrane, so that the only variable is the pH of the analyte solution on the outside of the membrane. So our potential that we would measure, so when we had our pH meters, remember it said, and you went to calibrate those pH meters, it said what was the voltage, and then you told it what that pH was. And then you put in a new value, and you put it into your pH 10 buffer, and the voltage changed, because it was really just reading the voltmeter. Right? It's really, pH meter is really just a sensitive voltmeter with a selective barrier on it. And what's neat about that is that because your charge on a hydrogen is +1 and it is the definition of like a +1 charge, right? You are directly measuring the activity of H plus in that solution. So from a physics and thermodynamic standpoint, not only is electrochemistry cool, but the fact that you're able to make this direct voltage measurement, which H plus difference is literally a voltage or a potential difference, that's kind of cool. Yep. So we're going to give this constant, and we're going to say it's plus beta, which is just going to roll in some of our constants, plus 0.0592 times the log of H plus on the outside. We're going to rearrange that to make it a pH. When we do that, we're going to take a minus, we're going to take our log and we're going to make it a negative. So we're going to take a P and we're going to make this minus over here. So it's going to be some constant, right? N times B, and then the pH of the outside at 25 degrees C. So brief history of this. 1906, the glass electrode was discovered by M. Kramer at the Institute of Physiology in Munich. In 1908, the first pH titration was followed with the glass electrode by Kemmelwitz and Haber. That was Fritz Haber at Karlsruhe. That is the Fritz Haber who did the Haber process. 1928, amateur radio enthusiast H.W. Wright at the University of Illinois used a vacuum tube amplifier to measure pH with a glass electrode. Because remember, these voltages and these changes in voltages are going to be very small because our pH is a log scale. In 1935, Arnold Beckman at Caltech invents a portable, rugged, commercial vacuum tube pH meter that revolutionizes chemical instrumentation. So the Beckman-Coulter Institute, you guys might have heard of them. pH is a hugely important measurement, and so since they were the first ones to kind of jump on this, they were the ones who kind of got the patents, and they were the ones who were to market first, so they made a lot of money. I think I can probably dig up some of these electrodes, but you'll notice that this is using this two electrode system that we saw in the beginning, not that compact combination probe that you guys are all used to. Okay. The pH glass electrode has to be calibrated. We did that in lab. We want to use two standard buffers, one with a pH higher and one with a pH lower. Just like any analytical measurement, you want to make sure that your unknown is being measured within the linear or calibrated range of the instrument. You don't have to extrapolate data to get there. The pH calibration should be repeated every 2 hours. Ideally, they should have the same temperature as the unknown. And you'll notice that you've got this negative slope again, right? Because it's a pH measurement. So our voltage is going to decrease as our pH is going to increase. In order for the pH electrode to work, the glass must be hydrated. All right, so remember this, must be hydrated. If I'm ever on you guys about, hey, don't let your pH probe dry out. Drying is dying. This is why. It needs that hydrated gel layer. If your pH membrane or your pH electrode membrane dries out, it's not going to work anymore. Right? You also have to have partial silicate production. That's why when you have to keep them from drying out. This is a reasonably selective electrode for H+. Other ions can cause a response. I remember I said we could trick this electrode. How are we going to trick this? Right? Other things that we need to do is we're going to take care of store and care for our pH electrodes. We're going to store it in an aqueous solution to prevent the dehydration of the glass. In order for it to work, the glass must be hydrated. That's why we have to keep them from drying out. If the electrode has dried, we can recondition it in dilute acid for several hours. Now, I don't want to sit around for several hours conditioning a pH probe. So that's why I'm going to say, hey, just keep those things in their storage buffer. If the electrode is to be used above pH 9, we want to soak it in a high pH buffer. If it responds sluggishly or cannot be calibrated properly, you can soak it in some a little bit more concentrated acid. Right? And if you have to, you can soak it into 20% by weight ammonium hydrogen fluoride as a last resort. I would just don't. Just go buy yourself a new probe. Messing around with that stuff is a recipe for disaster. You can do it if you're stuck on a desert island with Gilligan and some coconuts and pH probe measurement needs to be made. And then by all means use your ammonium hydrogen fluoride. But nah, I just buy a new one. Right. Where are we going to cause errors and uncertainty? Number one, is our standard buffer uncertainty, right? Our buffers are not going to be perfect. They're pretty good. We can set them to around 4 or 10 or whatever we want, but we're going to have some uncertainty of about 0.01 pH unit. We do have some uncertainty in that junction potential of about 0.01 pH unit. Right? We do have a little bit of drift error in our junction potential. We can have number 4, which is concentrated sodium error. Right? So this is kind of an important one. Now these guys are, this is just tolerance of the instrument. It's going to be plus or minus, 0.02 pH units, right? And this one is trickier, and sometimes it's controllable, and sometimes it's not, and sometimes it's unavoidable. But you need to be aware of that. So sometimes called the sodium hydroxide error. So if you're working and trying to measure the pH of concentrated sodium hydroxide, that should be really basic, right? But you're going to see a deviation or an error because sometimes these sodium ions, even though they're sluggish and will not ideally fit into those pores, it's going to be hard for them to get into those pores of the glass, but they can do it, right? Your pH will be artificially low. So you're expecting a pH of 13 or 12 or something, and it's going to read 11, right? And really you're measuring some of these sodium ions, and it's tricking your pH meter into thinking it's got hydrogen when really it's just sodium. Right? You could have a strong acid error on the other end. Glass electrodes underestimate the amount of H plus concentration in some strong acids. You can have an equilibration time error when measurements are made too quickly. You got to wait for this glass to respond, right? Ions have to physically migrate in these things. So you can't necessarily like stick it in and boom, take your reading right away. Right? Hydration of glass initialization error when you put a dry electrode in there. You could have a temperature error. This is also an important one that is correctable, but that sometimes people forget about. And then, it could be dirty. Right? Ideally, we don't want it to be dirty, but it could be. Right? So our alkaline errors when we respond to other small cations like sodium and potassium, right? And it's really bad when your sodium ion concentration is bigger than your hydronium ion concentration. If you got something like sodium hydroxide, your H plus concentration is really low, right? 1 times 10 to the minus 10 or something. But if it's in 0.1 molar NaOH, well then 0.1 molar is a lot more sodium than it would be H plus. Right? There's no response to the hydroxide. So when you're measuring something that's basic, remember you're not measuring OH, you're still just measuring H plus. It's just that you're measuring very, very, very small amounts of H plus. So here's an example of some of these errors in highly basic sodium hydroxide solutions where H plus is low and sodium is very high. The weaker electrode response to sodium causes a pH probe to underestimate the true pH of solution. So it's artificially low. And here are some different probes from different manufacturers showing what this error in pH is as a function of pH. So if you go up to pH of 12 on pore electrode number 5, right, you're thinking it's going to be 12 and it's going to only measure 11.5. Right? Number 3 over here is going to be even worse. It's only going to measure 11. And then over here on the other end, right, we got that acid error, right, where you're looking at this underestimating the H plus concentrations, right? So over here, it's going to appear a little bit more basic than it really is, but you got to go to pretty high acid concentrations, right? So if your pH is negative, if you're already dealing with a pH of -2, and you've got a pretty high concentrated strong acid, I'm probably not going to worry about being half a pH unit off. How accurate are they? Most careful pH measurements can have an uncertainty of about plus or minus 0.02 pH units at best, so about a 5% error. Measurement of pH differences can be more accurate with an uncertainty of about 0.002 pH units, but knowledge of the true pH will still at least be an order of magnitude more uncertain. So you can say, how did it change? Well, when it changed by 0.02 pH or 0.005 pH units, but saying really, what is it? Absolutely a little hard to tell. Here's just a quick example of some of those systematic errors. We're looking at acid rain and what the pH is called, what the pH is in different problems. So we've got some really low pH regions here, which are highlighted in green in both the US and in Europe. So reproducibility. When ordinary pH buffers were used for standardization, you ended up with some errors in there, and then they modified the standard buffers to match the low ionic strength of rainwater, and the inter-lab reproducibility improved. So they had a lot of variation up in here, right? And then they changed what their buffer system was. So that can actually be a problem with this idea of low ionic strength. So if you're trying to measure the pH of just pure DI water, it can be tricky because you don't have a lot of ions in solution for it to measure. And so the ionic strength of your buffer is going to kind of affect that a little bit. So that actually happened to me in lab one time. I was trying to make some measurements around a very low ionic strength solution, and to solve that, just added in a little bit of something to help change that ionic strength. Chapter 15-6, ion selection.